And the next thing, all right. So on Friday, we started working with Hess's law. Okay. And on Friday, we only did problems that you had to manipulate two equations. But I also said that today we're going to just step it up a notch. Okay? And so what we're going to be doing today is we're going to be looking at three equations. Now, you're also going to notice that with the two examples that we're going to look at today, that they like to throw you some curveballs every once in a while. They'll give you fractional coefficients, okay? Don't stress too much about it, okay? Because in the long run, all you're going to be doing really is adding or subtracting those fractions to have in our end result, okay? Some of the practice ones we're going to do Thursday and Friday, you know, they're not necessarily all going to have fractions as coefficients, okay? So don't stress too much. Let's take a look at this sample exercise that they have here, okay? Today, before we really get involved, you will need a calculating device, okay? So, if you have one, I would highly recommend you have her out. Okay, let's take a look. So we are to calculate the delta H for the reaction listed here. This right here is our target equation. So although it looks very, small in comparison to what we have to manipulate, it's going to all work out, okay? So 2 carbon as a solid plus H2 gas yields C2H2 gas. So again, that's our target equation. So let's start looking at our three reactions that we have to manipulate, okay? So again, always have a good understanding about what is in your target equation, okay? So let's start taking a look here. Is there anything in this first equation that we need in our final one? What do you think? Well, if we look, this first equation has C2H2 gas. Do we need that in our equation, in our target equation? Absolutely. But do we have to manipulate it at all? What do you think? Does it need to be changed? Does it need to be multiplied? Does it need to be reversed? Well, you notice that in our target equation, C2H2 is in the product location. In the first equation, C2H2 is, going to be on the reactant side. So it's not in the right side. So what I'm going to do to this first one is I'm going to flip this first equation. Okay? I'm going to flip this first equation. And what does that do to that sign on that delta H value? It changes it. So a negative now becomes a positive. Okay? And I'm going to show you these changes on the next slide. I just want to talk through these first. Okay, so we've addressed the first equation. Is there anything in the second equation that we need in our target equation? Well, I see a carbon there. Our target equation has a carbon as well. But what's the issue with the second equation's carbon? Compare it to the target equation. Exactly. There's no coefficient in this second equation. So what do you think we have to do to this entire line here? We're going to multiply it by 2. Okay? And so we're going to take this entire line. Again, what you do to this equation, all these coefficients, so we're going to multiply this entire line by 2. So then you'll have 2O2, 2CO2. Okay? But you also have to do the same thing to the enthalpy value. So you're going to take this and multiply it by 2 as well. And again, that's because enthalpy is an extensive property. When you start messing around and increasing or decreasing the coefficients, you're actually changing the molar quantity present in that reaction. So therefore, you have to do it. You have to multiply your delta H. Lastly, the third equation. Is there anything in the third equation that I need in the target equation? Well, I see that we have H2. That's also in our target equation. And I see that it's on the correct side of the arrow as our target equation. And the last thing I also notice is that the coefficient is the same. So it's got exactly what I need and how I need it. So this third equation, I am not going to touch. So let's recap. I'm going to flip the first equation. Therefore, change the sign on delta H. I'm going to multiply the equation and the delta H value by 2, so I can get a coefficient of 2 in front of this carbon to match the target equation. And the third equation, I'm not doing anything. So you'll have this. As we said, the first equation we flipped around. Change the sign. Multiplied the second equation by 2, as well as the delta H value. And then we left the third one alone. So much like what we did on Friday, and much like what we did on in our ionic equations way back last semester, we add up all of the reactants to one side. Again, if there's anything like O2s, go ahead and add them up. Okay. Then you add up the reactant side. And you'll notice that when you do that, and again, on our practice equation, I'm going to do this, adding and removing for you to show you. But when you add these up, you would see that there's 2 CO2, 5 halves O2, and H2O on both sides of the arrow that need to be eliminated. So after you've eliminated everything that's the same on both sides, you now are left with the target equation. And again, one of the last steps you want to do is after you've confirmed that all of your manipulation has matched your target equation, then solve for your delta H by adding all the delta H values together. So again, it's the same process as Friday, just adding one line. So let's look at an example here. Okay. So we have the target equation NO gas plus O gas yields NO2. You're going to need a little space. I highly recommend that you copy along with us. Okay. Stay. Okay. So we have 3 equations. We have the first equation, NO gas plus O3 gas yields NO2 plus O2 gas. Second equation, O3 gas yields 3 halves O2 gas. And then third equation, O2 gas yields 2 O2 gas. Okay, let's start tackling the items in our target equation together, okay? Let's look at our target equation. Where's NO, nitrous oxide, NO gas? Where do you see that in any of our equations? The first one. Perfect. So, do we need, first of all, is it on the correct side of the arrow? It sure is. Does it have the same coefficient? It sure is, does. Do I have to do anything to that first equation? No. So I'm just going to rewrite this. Again, sorry, you're going to have to come along with me as I rewrite this. Okay, so I might need to dim this a little bit. Okay. So again, this is our target equation. I'm just going to put a little star there. So again, we have NO plus O3 yields NO2 plus O2. And its delta H value is negative 198.9 kilojoules. Okay. Take a second to get that copied down. Now let's look at our next ones. Okay, so what we have remaining now is just O and then NO2. What you also notice about the first equation, what also did that take care of? NO2. 2 for the price of 1, folks. So what that is going to kind of tell me is that we're going to have to start arranging these other two to really eliminate things altogether. Do you see O3 in any of these equations? I mean, sorry. In the target equation, is O3 found anywhere? No. Okay. So we have to get rid of that somehow. And so you notice that in the first equation, I left everything alone. The O3 is on the left-hand side. What do you think I need to do to my second equation now so I can eliminate it? I'm going to flip the second equation. That way, they're on both sides of the equation, and I can cancel them out. Okay? So the second one, I'm going to flip. That's going to give me 3 halves O2 yields O3 gas. And again, when you flip the equation, you're going to change the sign. So now it's going to be 142.3 kilojoules. So I got rid of that negative sign. So there's just one more equation I need to address. Okay? Now's the third one here. Okay. Here, in the third one, I have O2 yields 2O. Okay? So we know that in our target equation, we have to have that O on the left-hand side. Okay? So what's the first thing I need to do to this equation? I need to flip it. Okay? So I flip it. I'm going to put this O on the left-hand side. My other question is, we've established that we have to flip it, but what do we also know about, look at the coefficients compared to the target equation? It's different. This one's a 2, and this one a 1, really, okay? So what mathematical process do you have that you can go from a 2 to a 1? Bingo. Divide. I'm going to divide this entire line by 2. So again, for the third equation, I'm going to flip and divide by 2. So when I flip it, again, 2 divided by 2, you're just going to have 1, or in our case, just oxygen as a gas. Yield, and again, the coefficient in front of the O2 was a 1, so 1 divided by 2, you get 1/2 O2 gas. And again, we divided the equation by 2, so we have to divide the delta H by 2. Now we also have to change the sign. It was a positive. Now it's a negative. Negative 247.5 kilojoules. Okay, so we have O gas yields 1/2 O2 gas, and divide the enthalpy value by 2 and change the sign. Now I'm gonna, as I go through and add up all the reactants and all the products, it's gonna take me a hot minute to go through everything. There's a lot here, okay? So I'm going to be moving the camera kind of along as I talk, okay? So the next step is, like I said, we have to add up the reactants of those 3 equations, add up the products of those 3 equations, mathematically cancel anything that we can, okay? So I'm going to start here. at the very first equation. I've got NO gas plus O3 gas. That's the last of the reactants there. Go move on to the second one. Plus 3 halves O2 gas plus O gas. And that's it for all my reactants. Okay. So then I move to my products. I've got NO2 gas plus O2 gas. Move on to the second one. Plus O3 gas plus 1/2 O2 gas. Whew. Okay. So again, just to recap, NO gas plus O3 gas plus 3 halves O2 gas plus O gas yields NO2 gas plus O2 gas plus O3 gas plus 1/2 O2 gas. Okay. Now, let's start taking a look at things here. Can I eliminate NO from this equation? Is it on both sides? Just NO? I cannot. It's only on the left-hand side. So I'm going to start rewriting this. NO gas. Okay. What about O3? Is O3 found on both sides? It sure is. Is it found in the same quantity? It sure is. So what can I do with it? Bye. Bye. Okay. Now let's look at O2. On the left-hand side, we have 3 halves O2. Now look at this side, the right side. The right side has 1 O2 and 1/2 O2. They're the same substance, so I can add those coefficients together. What's 1 plus 1/2? 3 halves, right? So I have 3 halves O2 on the left, 3 halves O2 on the right. What can I do with them? Cross them out. Okay, so we're making our way. Our next up is just O gas. Is O gas found on both sides of the arrow? No, it is not. So it just gets rewritten down here. And lastly, NO2 gas on the product side, that's all that remains. So it gets brought down. Does what I have left line up with my target equation? It certainly does. So now that I've confirmed that this lines up with my target equation, I can go ahead and do my last step, and that is sum up all of my delta H values. So I want you to double check my work, okay? So we should get a delta H value, again, after we've summed all these up, of negative 300, you can't see that, negative 304.1 kilojoules. And double check my work. Right? Yeah. Yay. Questions on how we do 3? It's just adding another step from Friday. Okay. And as you see here, as you start getting more lines, like 3 or more, I usually don't do any more than 3. But there may come a time to where one of your equations, you just have to arrange it so you can eliminate the entire thing. Okay. So that is Hess's law with 2 and 3 equations. Questions on that? All right. So we've got one more thing I want to talk to you about today. It is the beginning of section 7. You'll still need your calculators out. The last thing we're going to talk about is enthalpies of formation and enthalpies of reaction, okay? First thing we're looking at is enthalpies of formation, which is denoted as delta H with a subscript of S, or F, sorry. It's the defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. So this is simply the process that gives us these delta H values, okay? It's just the mathematical process that we can use to calculate it. We're going to be using that Appendix C. So if there are a few substances on that handout of Appendix C that I gave you, it should be in the back of your book as well, okay? So basically, we're going to be given reactions, and we simply have to access Appendix C and put the values in, okay? So this is a very important slide. As you see here, I have many asterisks. See that? Right there? Yes? Okay. So these standard enthalpies of formation are measured under standard conditions, okay? That term, standard conditions, might pop up next week under a certain exam, okay? And really what we say about standard conditions is 25 degrees Celsius, which is room temperature, or 298 Kelvin, and 1 atmospheric pressure. That's standard conditions, okay? Really all it's saying is these are measures that were determined during normal, everyday settings. So, again, we're using Hess's law, or at least the thought process behind Hess's law, that overall reactions actually consist of smaller step reactions, okay? So imagine this reaction right here at the very top, okay? It actually is going to be broken down into 3 steps, okay? And there's 3 steps are listed here, okay? Each one of these steps has its own enthalpy value, okay? Which, when you add them all up, equal the sum and the total of the normal everyday reaction. So we calculate this using this equation right here. I pointed this out about a week ago, if not a little bit longer than a week ago, saying that this equation is going to come back to us towards the end of the chapter, okay? Where we calculate the change in enthalpy by taking the sum of the enthalpy of formation of products minus the sum of the enthalpy of formation of products minus reactants. Wonderful, read. I got the first dose of vaccine yesterday. Didn't sleep well last night. Like, it wasn't like weird, it was like I was awake. And so I told my wife, like, my brain is a little slow to get up today. Anyway, now you'll notice that here we have N and here we have M. Those are really just the stoichiometric values from the coefficients from the equation. So one of the most important things you need is a balanced chemical equation. A lot of times you're going to be given the balanced chemical equation, okay? Our first example, they don't give it to you right away, but since it's the book version, they tell you, okay? Most of the time, though, you'll be given the equation. Before we get into looking at the sample problem, I want to kind of just go over real briefly Appendix C. You'll notice that on each page of Appendix C, you've got a column of substances here and a column of substances here, okay, in the middle. And in between those 2 columns, you have the information you're going to need. You've got delta H of formation. You've got delta G, which we don't need to worry about. And we have the specific heat of each substance. Now, you're going to find out quick that some of these may not, it's mostly listed in alphabetical order, okay? But sometimes, if I'm correct, if I think water was a goofy one, if I can recall. Yeah, water isn't under water. It's under oxygen. Okay? You also notice that substances like water or other substances have different states. They've got solid, they've got liquid, and they've got gas. You've got to pay careful attention to what state they are in the problem or in the equation. Okay, because that's going to change your value. So, going back to this equation here, I want us to take a look at the equation. I want us to find these, okay? So again, it's products minus reactants. It's the sum of the products minus the sum of the reactants, okay? So CO2 in Appendix C. So you'll just look up carbon. There it is, okay. Carbon, carbon dioxide, CO2 is located in the second column on the first page. Okay, and you see that it's got a delta HF value of negative 393.5. See that? See that there? That matches that number. But what does that 3 come from? Where does that 3 come from? So, you're going to take your coefficients and multiply them by the delta HF value you find in Appendix C. Again, H2O. H2O has delta HF value. Again, it's liquid. And that's, remember, H2O is under oxygen. So it has a delta HF value of negative 285.8 kilojoules. Again, where'd that 4 come up from? The coefficient. Carbonization. Okay, so that's all the products. Again, you see we put them in brackets because we're going to sum them up after we've multiplied them. Minus our reactants, C3H8. Ouch. You'll find that underneath carbon as well. It's got this value, and again, it's just got a 1. But the one I really wanted to point out to you is oxygen. Okay? Oxygen, in this case, is listed in the reaction as its elemental form. Its most stable elemental form. So, you will not find a delta HF value for elements in their natural form. Okay? They do not provide any enthalpies of formation. So it just gets a big old donut. So once you've got everything listed here, go ahead and multiply the coefficients through. Excuse me. Add them up, subtract, and then you will calculate your enthalpy value for that reaction throughout this process. Now, we are out of here in 7 minutes, okay? I want to just take a quick look at our practice problem here, and we'll go back over it tomorrow, okay, before we get through some additional exercises, okay? So we're not going to worry about problem B here. We're just going to focus on A. A says calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6, liquid form, to CO2 gas and H2O liquid. Okay, this is one of those rare instances where you are not told or given the reaction. But if you are needing to, it's a combustion reaction. So you're going to take the C6H6 and react it with O2. Now, I'm glad they eventually give us this equation because when it's all said and done, this is what equation you'd go with. C6H6 liquid plus 15 seconds, 15 halves, if you will, O2 yields 6 CO2 plus 3 H2O liquids. A very weird equation. So this is the balanced equation. So in order to solve this again, we're going to take our products minus our reactants. So again, using Appendix C, again, you've got 6 CO2s, 3 H2Os as your reactants, minus C6H6 plus 15 halves of O2. So start looking these up. You'll notice that, again, oxygen's present here. You're not going to worry about that. But since it's a combustion reaction, you're going to have some fairly large negative values here. Okay. Now, I wanted to do one. Usually we have time to do one, but not this year in today's discussion. So tomorrow, you will come in. We're going to do, again, a brief run through of the steps for solving these. We're going to do a practice problem in this format. And then what we're going to do is we're going to do another question very similar to this, except we have to calculate the enthalpy of formation for one of the substances. Not the overall reaction, but one of the substances. So really, it's just a kind of an algebra, a very basic algebra problem. Okay, so again, we will talk more about this tomorrow. You'll also be given your worksheets that we're going to be doing Thursday and Friday. Those of you at home, I thank you for joining in, but at this time, you can go ahead and sign off.